Hello everyone, my name is Hanchao Liu. This is my paper presentation for course CS 6263. The title of the paper is Grid Shock, Coordinated Load Changing Attacks on the Power Grid. So this paper presented a method of building a bottomnet of zombie computers and modulated their power assumptions by utilizing different devices in a coordinated way to attack the power system. So the outline of the presentation is the introductions, which will talk about the background of the power system frequency regulation and also a brief introduction of the attack method. Then follows the threat scenarios of the load modulation attacks. 3 different types of attacks will be discussed, and the feasibility of this grid attacking botnet will be discussed as well. Then we will evaluate the power modulation of those devices, basically how much power each PC can change rapidly, and also the power changing capability of other appliances that are connected to the PCs on the internet. Then we will evaluate it when those devices are controlled by a bottomnet to attack the grid, how the grid will be affected. Those three types of attacks will be evaluated as well. Then we will have a short discussion, and the future work will be discussed as well. First, introduction. So in today's power system, the power generation and the load consumption are balanced at any time because the electricity cannot be stored in large-scale power system. Any imbalance of the power system, power generation and load consumption will be reflected as a frequency deviation. Basically, when the power generation is higher than the load assumption, the power system frequency will increase. And when power generation is higher than the load consumption, the power system frequency will increase. And when the power generation is lower than load consumption, the system frequency will decrease. And to regulate the power system frequency, or we can say about regulate the balance of the power generation and the load consumption, there are 3 levels of controls that are involved: then primary control, secondary control, tertiary control. So this diagram shows how primary and secondary control works. So for primary control, the power system generation means large generators are programmed or predefined to output their output different power at different frequencies, following predefined curves. The curve is when the frequency decreases, power output of generator will increase, and when the frequency is lower than a certain point, the secondary control will hit in. The secondary control will move up this operating curve of the generator. That means at the same frequency, the generator will output more powers. So this diagram shows how the primary and the secondary control works when there are grid events. At this point, a grid event occurs. It could be a load step increase or generation step decrease. As we can see, because there are less power generation than power consumption, the frequencies start to decrease, and then the primary frequency control start to hit in. It will increase the power output, and because the power output increase, the system frequencies start to recover. However, the primary control cannot bring the system frequency back to the rated value, and then after a certain amount of time, it's roughly 30 seconds, secondary control start to respond. It push the generator to output more powers and bring the frequency back to the rated value. The tertiary control is much slower control compared to primary control and the secondary control, and more often than not, it requires the system operator manual intervention. So the frequency stable is very important. If the power system frequency is deviated from its rated value, either 50 or 60 Hertz, depending on different countries, it will cause the load to be shedded or even generator to be shedded. So this table shows an emergency routine in case of under frequency in Germany. Their rated frequency is 50 Hertz. So when the frequency is below 49.8 Hertz, it will start to shed part of the pump's load. And when the frequency is below 49 Hertz, it start to shed large amount of load. When the frequency further decrease, say below more load will be shedded. And when the frequency is below 47.5, even the generator will be shedded to prevent the large power plant from permanent damage. So in this paper, a load modulation attack is proposed. So it assumes that hundreds and thousands of computers and other smart devices will be controlled by a bottom-net. And this bottom-net will regulate the power consumption of computers and smart devices to increase and decrease rapidly, so in a coordinated way. Therefore, the power system load will start to increase and decrease periodically, and which is in a modulated way. However, the power generation or power supply from the large power plant cannot respond as fast as the load change because of its mechanical stress and control design. And therefore, the load, the power generation and the load assumption start to unbalanced, and this will cause the power system frequency start to deviate from its rated value, and this will cause the load shedding and even generation shedding, as mentioned before. So this new load modulation attack, it does not rely on smart grid features, and it only uses existing internets, PCs, printers, and maybe even smart devices such as Internet of Things. So next we will discuss about the threat scenarios of load modulation attacks. The goal of this attack is, as mentioned above, is to rapidly change the power consumptions of the PCs and to cause frequency deviation, and then further cause generation and load shedding and even transmission line trips. 3 different types of attacks are defined. The first one is type 1 stack. It's called static load attack. It will increase the power consumption of all the infected PCs to the maximum value. So this attack is targeting at the primary control. So the second type of attack is the dynamic load attack. It will modulate the power consumption of the infected power based on the power system response time, mainly the primary control. So as we can see from the diagram, the difference of 2 different attacks. So type 1, it only just step up the power consumption of the infected PC. While in the attacked type 2, the power first, the power assumption of the infected PC first increases and then wait for the roughly 30 seconds when the primary frequency control to regulate the power, and it will then decrease the power assumption. Wait another 30 seconds and then step up the power again. So by modulating the power consumption, it can increase the effects of the effects. It will increase. It will amplify the effect on the system frequency deviation with the same amount of power attacked. In the so another attack is the interzone attacks. So this attack aims to trip the transmission line that are connecting areas by putting large amount of load on this transmission line. So this kind of attack is targeting at the secondary control. As can be seen here, before assuming there are two control zone or interconnected area Z1 and Z2. Before the attack, Z1 has a power generation of P1. It has demand D1, and T is the power transmission from Z1 to Z2. And in area Z2, there are P2 power supply plus T power from Z1 and the D2 demand. As an attack increased the power demand in Z1 by M, and as a result of the primary control, the power supply from the area Z1 will increase 1/2 of M, and the power transmitted to Z2 will reduce half of M. Here it is assumed that this power will be distributed equally between the increased supply and the transmission line. But in actual system it might be different, but it will not affect the analysis. As a result, the secondary control will hit in to drag the power transmission back to T by increasing the power supply in the zone area to M plus P1, and reduce the power supply in the area in the Z2 by 1/2 of M, and it will return to pre-attacked value. Then at this moment we can remove the attacked power in area 2 and move it to at this moment we can remove the power increase in Z1 and move it to Z2, and all this M power will be transmitted through the tie line, because the primary control is agnostic to the shifts of the modulated power. And we can see the transmission line, the transmitted power is increased. It's a large burden to the transmission line, and it could trip the transmission line. So next we will discuss the feasibility of this grid attacking botnet. Basically, whether we can make this work to generate load modulation. First, the acquisition of the botnet. The price is very important. It varies, but roughly from $400 to $1,000 we can get 10,000 of bots. Another issue is the synchronization. Because we want hundreds and thousands of PCs to increase and decrease their power assumption in a synchronized way or coordinate way. Therefore, we already have the modern protocol such as NTP. It provides sub-millisecond performance and therefore we have enough accuracy, because the fastest primary frequency control follows to 30 milliseconds. Another is when we want to, if attacker want to launch a inter-area attack, the type 3 attack, geographic estimation is important. To achieve this, there are different tools such as GeoIPs, Wi-Fi localizations, and sometimes even the keyboard layout of different PCs can provide physical location information. Another important is the power system frequency measurements. This can help to maximize the attack effects. There are already many low-cost grid frequency measurement units which can provide local frequency frequency measurement. And further, if some remote attacks can even leverage the audio or microphone hams and the webcam light flickering to estimate the remote power grid frequency. So another important thing is to measure how much one or individual PC can change their power and how fast it can change. So this is measured in a lab environment. It can be seen here that with a low-end PC, the power supply can ramp up within 2 to 3 AC cycles, and with a high-end PC, that the power can ramp up within one AC cycles. And for this diagram shows power change of TFT screens. It roughly takes 8 seconds before it goes to sleep mode, and there are also some other load alternating appliances such as laser printers and Internet of Things such as smart appliances. So this table summarizes different devices can be leveraged to modulate the load. It includes CPUs and GPUs. They have much faster response with very low latency in on and off times, but they have relative low power change, except for the high-end GPUs, which has roughly around 150 to 300 watts of load change capability. The rest screens and laser printers and other smart devices, they have large rating to change the power, but their response time are relatively slow. But the response time is relatively larger, but still like below 30 seconds. So this next we will look at the grid frequency response to different attacks. First, a simplified power system model is used, and for the attack one, only the primary control is included. So this one it uses a static load of multiples of reference incident of 3000 megawatt, basically 3 gigawatts. And this plot shows simulation results. If we look at one diagrams, different static load attacks of different attack level compared. The first one is the 0.5 times of the reference incident, like 1.5 gigawatt, and 1.5 times and 2 times, and the intact the attack power increasing. As we can see, to cause a trip, which means the frequency is below 49, we need the minimum power required in this case is the two time of the reference incident. So if we look at these three diagrams, they are comparing the attacked effect with different power level, grid power level. As we can see, the more the network power, the less effect the attack will have. And if we compare the plots on the upper and the lower, they are telling us different effects of different renewable energy penetration. Here I want to make it clear that because of the higher level of the power penetration of renewable, the power system will has less inertia. As a result, it is more vulnerable to any load change. Basically means that the same amount of load change will cause larger frequency deviation, as we can see in this case with higher renewable energy penetration, even 1.5 of the 1.5 times of the reference incident power can cause a trip in the system. This one shows the attack type 2. You can see in this case only it can be it permits to be more successful than static ones, saying that reach higher frequency shifts while modulating the same amount of load. Here in this case, we only change 1.5 of reference incident. So we first increase the power consumptions and wait for 30 seconds, and then remove this power downturn increase, wait another 30 seconds, and then increase, and keep repeating it. As a result, we can see that with only 1.5 of reference incident, the frequency deviation will be below 49 Hz and cause a trip. And it shows that dynamic attack has a large effects than static ones. So for attack type 3, because it's targeting the secondary control, so the secondary frequency control are modeled, and the two area of power system are modeled as well. So this attack is first we increase the power consumption in area 1 and wait for roughly 120 seconds. So make sure that secondary frequency control will hit in, and then reduce the power consumption in area 1 and increase the power in area 2. As we can see here, the frequency change is relatively low because the system is much larger. However, our target is to increase the power through the transmission line. As shown in this diagram, we find that the power transmission change dramatically, and it will trip the transmission line. So in this paper, there are some further discussion about different ball scenarios, and it shows that roughly 2.5 to 9 million of infected devices is enough to cause a trip in the European network. Because of the time, we will not discuss into detail, and the future work will include a more sophisticated power system model to get accurate frequency response, and also the cascading effects can also be studied with more sophisticated grid model.